Topic today, growth functions. So we need to, do the abstract analysis. So we need to use some abstract notations to describe efficiencies of algorithm in a compact way. Because when you describe algorithm efficiencies, you do not want to use a lot of words. You do not want to use some complicated notations. So you want to use some relatively simple notations, but those notations can represent, some specific meanings in a concise way. All right. So let's start learning those abstract concepts. B.1, introduce growth functions. This concept. All right. Let us consider formula between running time and a number of basic operations. So here, what we are doing here, we measure efficiencies. We measure efficiencies of algorithms. When we do that, we learned before. There are two ways we used before. The first way, running time or response time, right? So after we hit the enter, start running our program, so we clock it. We look at the execution time, okay? So that running time, that's the direct measure. Straightforward, direct measure. But that measure has a problem. It's not stable. This measure not stable. So why not stable? Because the machines running this algorithm could be different, right? Some people use some low-end machines. Some people may use some super powerful machines. The result, execution time could be very different. The difference could be pretty big. So we cannot use this direct measure for a comparison. Okay. So later, we want to switch to a stable measure. So the number of basic operations. So the second one, then this one you can see it does not rely on the machines, right? So you use supercomputers, so you use some, low-end computers. You need to use the same number of basic operations. All right. Here, let us compare these two different measures. And here, we do not want to compare their difference. We want to connect them. They are closely related. These two measures are closely related. So we want that connection. We want to see that connection here. All right. First, let us use some appropriate notations for these two measures. All right. The first one, function of the running time, T of n. N is the problem size. Yeah. So we're familiar with this way, problem size concept. Okay, yeah. T, yeah. Time function. Yeah. All right. For the second one, function of the number of basic operations used, C of n. Yeah. C because we do counting. Okay, we count the number of basic operations. Yeah. So what is this concept? Here we use a concept called the basic operations. Yeah. Yeah. Its meaning is like this. The operation contributing the most to the total running time. Yes. Yeah. So if you recall the polynomial evaluation problem, we work on two types of operations, addition and multiplication. Multiplication contributes the most, right? So we treat the multiplication as the basic operation. Yeah, so that when we do the measuring, we only count the basic operations. So here you can see we ignore other relatively, or we call them minor, those roles, those operations, they play a minor role. So not a major role. Yeah. Basic operation, this one, it plays the major role. So we only look at the basic operations. Yeah. All right. Then another concept, we need to use a special notation. So that is execution time of basic operation. Little c with subscript OP. Yeah. Because each basic operation, its execution time on different machines could be different. Yeah. Supercomputer, low-end computer, this number is quite different. Yeah. Even if it is so different on different machines, but we can treat it as a constant. So it's a constant number, right? Yeah. No problem on that. So it's a constant. So that means on a particular machine, there is a constant associated with this machine. Right? So then we can use this constant all the time when we run different algorithms on this particular machine. Okay, so we do not worry about it. Yeah. All right. Yeah. So it's not like at different time you run your programs on the same machine. This constant will be different. Yeah. This constant will be the same. Yeah. All right. So with this assumption, then let us do the discussion here. All right. Formulas. Let us compare these formulas. Yeah. Here we take an approximation approach, not because we ignore those minor operations, right? Yeah. So that's already an approximation step. Yeah. So our approximation formula is like this. T of n approximately equal C op times capital C of n. Yeah. That's straightforward approximation. Yeah. All right. So we use this approximation formula to get connection, relationship between these two functions, T of n and capital C of n. Yeah, all right. And first, we observed this property, simple property. These two functions are proportional. Yeah, because, you know, their ratio is just a constant. Little c of, that is a constant. Okay, yeah. Proportional, yeah. That means these two functions are closely related. Yeah. The connection between them is just a one constant. Okay, one positive constant. Yeah. So we can a little more accurate. It's a positive constant. Yeah. All right. All right. Yeah. And in these two functions, T of n, C of n, we will using C of n instead of T of n. Yeah. And the C of n, this function, the good thing is we just count the number directly, number of basic operations directly. Yeah. So that's most of the time, that's very convenient. Yeah. We do not need to clock anything. Right? Do the counting. Yeah. Do the counting even if we do not run our program. Yeah. We can count the number of basic operations. Yeah. But for T of n, you cannot do anything without running your programs, right? You have to run your programs first. Then you can find the value of T of n function, but C of n is not. Okay. When we have the details of our algorithms, we can do the counting already. So we do not need to run our programs. So you can see which one is more convenient. Okay, yeah. All right. But we like to explore the relationship between these two functions a little more. Okay, yeah. All right, so here the approach we take, we ignore unnecessary details. Yeah. Yeah. When we do the switch from T of n to C of n, and later, when we have our discussion on C of n, we need to ignore some more details. The purpose, the objective is we want to make our representation simpler, easier, but still our approximation is good enough. Here, we use approximation, right? Yeah. But we also want to make our approximation as good as possible. Okay. We don't want to have a bad approximation. We want to have a good approximation, as good as possible. All right. Yeah. So later I'll try to convince you how good is the approximation. Okay. How good is the approximation? Actually, very good. All right. Yeah. But we need to ignore some unnecessary details, less important details. Yeah. The first thing we can ignore, this one, can we ignore some constant? Can we ignore some constant? Yeah. Here, to show you some example, for example, you know, m plus 4. Here, 4 is a constant. Yeah. When we do the comparisons, when we want to look at how fast is our algorithm, can we ignore this constant? All right, so, and let's see another example. 1/2 n squared, right? This 1/2 is a constant, right? Yeah. When we want to get an idea, how fast is this algorithm? The question is, can we ignore this constant? Yeah, these two cases here we can consider. All right, yeah. Second, can we ignore some minor terms? Some minor terms. The minor terms here, if I show you one example, let's say n squared plus 2n plus 3. We refer these terms as the minor. Yeah, terms. Right? Minor terms. Yeah. Can we ignore these minor terms? Yeah. All right. Yeah. All right. First, let us take a special view. So this view we take, we do the ratio of, for these two functions, T of n, C of n. But when we do this special ratio, we double the problem size. 2n, we double the problem size, input size, and problem size. Okay, yeah. After we double the problem size, then we take the ratio for each individual function. Okay, T of n. T of 2n over T of n, the first ratio. And T of C of 2n over C of n, the second ratio. Yeah. We can see if we go back to the original formula, the constant can be canceled out, right? The constant can be canceled out. So these two ratios approximately equal. Yeah. Why this view is good? This is a good view. Yeah. So we treat this as a good view. The first reason, the constant C op is gone, right? Yeah. In this formula, the constant little c op is gone. So that's good. That's a good property, because here it tells us if you look at this ratio, then the computer factor is gone. The hardware, the computer factor is gone. A fast computer, a slow computer, it doesn't matter when you consider this ratio. Yeah. But from another angle, so this ratio can tell us some useful information. How fast your algorithms increases when you double the problem size. It tells you that information. So that's kind of, some useful information to tell you how fast your measure function increases. Okay, so that information is useful. If your measure function increases very fast, grows very fast, so then that means your algorithm slower, right? Yeah, because the function value grows faster from the T side, faster, it uses more execution time, it's slower, right? From C side, you need to use more, number of basic operations. It also means slower, right? Yeah, so you can get that information easily. All right, yeah. So how fast it changes, how fast the measure function, changes when the problem size is double. Yeah. So that gives us some good reason to ignore this kind of constant. This kind of constant, because when we take the ratio, it's gone. Okay, it's gone. That tells us we have a good reason to ignore this kind of constant. Okay, yeah. But how about that? Yeah, later I will explain. Yeah, so we have also good reason to ignore this kind of constant. Yeah. All right. Yeah. So let me go to the next one. Introduce the growth function concept. So with the discussion in our previous slide, now in this slide, we need to introduce a basic concept, growth function concept. Yeah. Yeah. All right. Question. What is the major term in an efficiency function? Yeah. First, when we use this concept, what do we want to do? We want to measure efficiency of our algorithm. Now, because we know efficiency of the algorithm, usually we have a function expression. Okay, yeah, it is a function of the problem size. We have that function. All right, yeah. After that, yeah, we want to make our function as simple as possible. So we need to simplify it. Yeah. So we have an original expression, but usually our original expression not very simple. Yeah, it looks pretty complicated. Yeah. So it's not easy to do comparisons if the expression is very complicated. For easy comparison, so we want to simplify it. Yeah. Here, this growth function concept, we want to simplify our original efficiency function as much as possible. Yeah. All right. So let me show you. The way to simplify it, first we need to identify the major term. Okay. Yeah. The major term, we use the dominant term before leading term, right? Yeah. I remember Sarah used that first in this class, the dominant term, leading term. Yeah. So when we look at polynomials, we have leading term, right? All right. Yeah. Recall the selection sort. Yeah. In selection sort, we sort the array, yeah, in this special way. So the efficiency function, this is the efficiency function. Okay, yeah. In this efficiency function, if we expand it, so we have two terms. The first term, 1/2 n squared term, and the second term, minus 1/2 n. And we consider the leading term, that is the dominant term. Okay, yeah. So we take that dominant term to do our first simplification. Okay, so we throw away the remaining terms. Okay, only keep that leading term. So that is the first round approximation. Okay, how good is this approximation? So later I will convince you this approximation is very good where n is large. Okay, yeah, where n is large, very large. Okay, all right. So here, dominant term, we take the dominant term from the original function. That's the first round approximation. All right. Then you can see in this dominant term, you have that 1/2 constant. 1/2 constant. Based on our previous slide, when we look at the ratio of those two functions, when the problem size is doubled, this constant is not important. It is canceled, right? Yeah. So then we do a second round approximation by ignoring this 1/2 constant again for another simplification. Yeah. All right. So we get another round simplification. Yeah. And square, and we call this one the growth function. Because that is pretty simple, and this function reflects how fast our algorithm is. Pretty good, yeah, in a good way, yeah. And it is an easy function to see how fast is your algorithm. Yeah. So that's the reason we use this growth function concept. Okay, all right, yeah. Next, I want to convince you when we ignore the minor terms, it's not a big deal. Now, our approximation is still good. Now, after we throw away those minor terms, our approximation is still good. Now I want to convince you this point, okay? So I like to do some calculation here, all right? Oh, did you see? Yeah, I show a formula, but on my screen, it does not show up. I show some oh, what's wrong with it? Oh yeah. It appears after long time, 10 something seconds. Yeah. All right. Yeah. Here, what I do, I compare two terms. The first term, second term, I take the ratio. Yeah. Here, I got a message from my side that my internet connection is not very stable. Yeah. All right. And when I take the ratio, I take the limit when n goes to infinity. Yeah. Here you need to use your knowledge, the limit, how to calculate limits in your calculus. Yeah. But this limit is very simple. Yeah. First, we do cancellation as much as we can. 1/2, the constant part cancel out, and n squared n, after cancellation, we only have n left. And when n goes to infinity, this limit also goes to infinity, right? Yeah. It tells us, if you look at the ratio, how dominant our first term is. This limit infinity tells us the dominance. How dominant the first term over the second term. Okay. Now, by convincing argument, yeah, this infinity, we know it is larger than any particular number, right? Yeah. So suppose this function give us the measure number, efficiency measure number. All right, yeah. And we look at in this measure number, we look at the, percentage of first term, second term. There is a percentage, right? Contribution percentage, first term, second term. Yeah. But where n is very large, n goes to infinity. When n becomes larger and larger, the percentage of the first term becomes larger and larger. And with the dominance, because the ratio goes to infinity, so you can see the percentage of the first term will be 99%, very close to 99%, many nines, right? Yeah. And the second term, the percentage, the second term percentage 0.00, yeah. Many zeros. Okay? Yeah. Because the ratio goes to infinity, right? Ratio goes to infinity. So you can see the contribution of the second term will be closer and closer to zero. And it could be ignored, right? Yeah. If the contribution is so little, we can comfortably ignore those minor terms, right? Yeah. So from this simple calculation, yeah, so we can see when we do that kind of approximation by throwing away minor terms, our approximation is still very good, right? So good, we just throw away this little part, right? We didn't throw away too much, right? Yeah, but under the condition n goes to infinity, that is the condition. When n goes to infinity, yeah. So here, in order to convince you completely, I need to make another argument. This n goes to infinity. So that is the most important thing we are looking at. Yeah, we are looking at when n goes to infinity, when n is very large, larger and larger, we worry about that part. That is our most concern on that part. Okay, so that is another argument. Here, we do not have enough knowledge to see that. Yeah. So I need to, after I give you some more concepts, then we can see that. Okay, yeah. In our part C, so we will see that when n goes to infinity. So that's the hardest part we need to worry about. When n is relatively small, we do not worry about that. Okay, so in other words, so when n is relatively small, okay, yeah, we do not worry about the measure. All right, yeah. So this point, so we will see this point in our part C. Okay, part C of this module. Okay, yeah. So our biggest concern is this part when n is very, very large. That's our biggest concern. Okay, all right, yeah.